So we're going to talk about EN 8177, which is the standard on lift subject to seismic conditions. Before we really talk about that, let's talk a little bit about earthquakes and what causes them and the importance of that. So if we look at the surface of the Earth is made up of these, wrong way here, is made up of these plates, and the plates move around, and they collide with each other, they move past each other. And the earthquake that we had this morning or yesterday in Mexico City was here on the Cocos Plate and the North American Plate. And so those plates happen to have what's called a convergent boundary. And a convergent boundary is where the oceanic plate goes under a continental plate. Oceanic plates are more dense, and so because they're more dense, they're more heavy, they slide under the continental plates. And what you have associated with those is you'll have volcanoes on the coast, and you'll have this subduction of the crust going down underneath. And so as it goes down underneath, there's a lot of friction. Actually, the Cocos Plate is moving into the North American Plate at a rate of 76 millimeters per year. Doesn't sound like much, but in 12, 14 years, it's a lot. And it's a tremendous amount of mass moving under. There's a lot of friction, and the friction causes the rocks to melt. The rocks melt, then they get lighter, and then they form volcanoes. And this is what you have in the Mexico City. You have that along the entire part of southern Mexico and places like Costa Rica, and we're all familiar with volcanoes there. So you get these strong earthquakes. There are other convergent boundaries, and this is where you have two oceanic plates. So they collide, and what you end up with these is a series of an arc of islands. And you see this island arc in the Caribbean. Technically, I guess you would say the islands of Japan are an island arc. Kamchatka Peninsula ends up with an island arc off of it, and the Aleutian Islands are island arcs. So these create earthquakes and volcanoes. The volcanoes are in the ocean, but they reach the surface and they become islands and in some cases countries. And then there's another type of convergent boundary, which is where you have two continental crusts, and they run into each other, and then they form mountain ranges. So probably the most interesting one there, the most notable one there would be the Indian Plate colliding with the Asian Plate, and you have the Himalayan mountains. And we have lots of earthquakes. We had an earthquake in Nepal just a few years ago related to that. So these are convergent boundaries, but there's a couple other boundaries that exist. One of them is, these are transform boundaries, and that's where one plate slides by another plate. They aren't really colliding, they're just sliding. And the one that I'm most familiar with is the San Andreas Fault in California, because it creates lots of earthquakes. And there's one plate is moving north and the other plate is sort of stationary. The relative movement is what you see here. One moving this way, one moving that way, and lots of earthquakes. There's another type of, there's something else called a divergent boundary. And this is associated with, particularly in the Atlantic Ocean, the Mid-Atlantic Rise, where you have these two plates that are moving apart from each other. And so you have, what fills in the void is lava, volcanic rocks coming up from the surface. Generally, these make small earthquakes, but there's one exception to that, and that's Iceland, because it's right on the Mid-Atlantic Rise, and of course we know there's lots of volcanic activity there, and there's also a lot of earthquakes associated with that as well. Talking about EN 81, the aim of EN 81 is to avoid the loss of life and reduce the extent of injuries associated with lifts during seismic conditions, earthquakes. We want to avoid trapping people in the lifts, obviously, and we want to avoid damage, just in general, and we want to avoid environmental problems related to oil leakage with hydraulic elevators. Additionally, we want to reduce the number of lifts out of service, because when the earthquake is over, we're going to need those lifts to move people into hospitals and things like that. So part of it is to make these more survivable. So EN 8177 identifies these hazards. And so one of them is the snagging of ropes, belts, traveling cables. So what happens is that during the earthquake, everything is moving around, the ropes start moving around, and they can get hooked onto rail brackets. And then that's not so good because it can destroy the ropes, or it can destroy a traveling cable, and then the lift will not function. Another one is car frames leaving their rails. So here's a picture of a car frame that is actually in Chile that left its rails. So here's the rail, and here's the roller guides, and you can see they're not in the guides. And so the problem with that is that ultimately the car and the counterweight might get together in an unpleasant way. So that's one of the hazards that is addressed here is how to keep car frames within their rails. Another one is counterweight frames leaving their rails. That's a serious problem. And here's a picture of a counterweight frame that left its rails. You can see it has sliding guide shoes here. Here's the guide rail, and it's free to collide with a car or anything else it wants to collide with. Another hazard is counterweight filler weights leaving their frames. And here's a picture of what's happened here. If you take a look right here, these are subweights, and they've fallen on top of the car, and it looks like they actually did some damage here. Would you like to be on top of a car when one of those fell down? It would be very unpleasant. So this is something that one of the goals is to keep these subweights within the frame so that they don't fall. So the other thing we look for is hydraulic pipe rupture, because if the pipes rupture, you're going to have oil everywhere. It's an environmental issue, but it's more than that, because oil, although hydraulic oil isn't particularly flammable, it can catch fire, and it'll just be another problem. And then you have the general pollution related to the pipe failure. The other part of it is the hydraulic tanks. They're filled with oil, and if they rupture, you're going to have perhaps environmental damage. Now, there's a trend in the industry to switch to vegetable oils, which are if they get away, they're non-polluting, but it's still a problem. You just don't want this to happen. There's also large guide rail deflections, and that's one of the things you want to eliminate. And here's a picture of a guide rail that you can see it's quite well deflected here, and it's outside of the guide shoes. So this creates the problem of now the counterweight is free to move wherever it chooses to move to. So in addition to large guide rail deflections, we are interested in machinery anchorage failures. Now, I've seen this in California many times, and here's an example of this particular way of attaching the machine just wasn't up to the level of the earthquake, and as a result, the steel bent and the machine can move around. Here's another example where the controller fell over, and so you have to think about how do we anchor controllers in earthquakes so that they don't fall over. And so additionally, EN 8177 addresses limit switch and landing switch damage, how to prevent that. Because if you want the lift to go back in service, you don't want these devices to be inoperative. You want them to function properly. And so this has to be considered in the code. And then loss of electric power. You're going to have, you can anticipate losing power. How do you keep the lifts running in the absence of power? You have backup power systems. And so in the code, it comes up with something called a design acceleration. And this is what we have to do. How do we design for the accelerations that the lift equipment's going to see when we have the earthquake? And so this has what appears to be a complicated set of equations, but they really aren't. And so this is the design acceleration that you have to design to. This S sub A is this here. And what really happens is with design acceleration, this value here is actually a constant, and it's 2. So you can simplify the formula quite quickly. The other thing is this block of this equation basically has to do with when you have a situation where the lift machine is very heavy at the top of the shaft, and so it enters into the oscillation frequency of the buildings. But most applications, this isn't really a factor, and so this reduces to 2.5. So now it becomes quite a bit simpler formula to look at, and this is what you end up with as the final formula. This A sub D is the design acceleration in meters per second. This is what the equipment has to be designed to withstand. Then you have A, which represents the ground acceleration that you would expect to get from an earthquake at the particular site. And it varies obviously from site to site. And we'll take a look at a map in a little bit of Europe, and you can see what that is. And it's in a particular location with what's called type A soil. Type A soil is rock. And then, well, G is gravity. S represents the soil type. And so there's a value that's a multiplier if you have soil that is not other than rock. And then this final representation is the importance factor of a building. Now, not all buildings are equally important. Probably the most important buildings to survive an earthquake would be hospitals. But we're not overly concerned about things like barns for horses, except unless they're race horses. So we'll take a look at what this is. This is the European seismic hazard map, and the darker colors here are the areas with high anticipated accelerations. So you can see the UK, most of France, most of Germany, Scandinavia, not a lot of seismic activity. But start down the peninsula here in Italy, go to Greece, go to Turkey, and you can see there's a lot of seismic activity, and you can expect to see, and we all know there's been recent earthquakes in Italy. There's always earthquakes in Turkey. And so here's a map of Cyprus, and this is a more detailed map, and these maps exist for most countries. And you can see here, this area here is the one with the highest accelerations to be expected, the yellow the lowest. So if you were going to build a building in Larnaca, you would have to use this value here. So when you talk about design acceleration, we talk about the types of soil. So type A soil is rock, and it has a value, a multiplier of 1. And if you get very surface alluvial layers on top of stiffer material, it goes up to 1.4. Now, in this earthquake in Mexico City is built on a lake bed, and so it's a very recent alluvial soil that also is subject to liquefaction, where it's like during an earthquake, the groundwater makes it into mud and buildings sink. So it would be, if you were applying this in Mexico, you would apply the value of 1.4. Now, building types this is something that a country can modify, but these are like the recommended values, but a particular country can change their mind. So these buildings, we don't really concern ourselves. Ordinary buildings have a value of 1. Building whose resistance is important, like schools, assembly halls, 1.2, and hospitals, fire stations, power plants, 1.4. So it's like 40% more accelerations are expected with this. Now, again, this is subject to each country can change these values, make them bigger. So, for instance, in California, where I'm from, we follow the ASME code for seismic, but then California has their own for schools and hospitals, and then you have to have much higher standards for schools and hospitals. You have to have a structural engineer design your rail brackets, your rail calculations. You have to submit them to the state architect, and then he has to approve them. And so it's because California thinks we really want to keep our schools and hospitals, safe. And if you look at buildings there, you'll see, like in San Francisco, you'll see a lot more structural steel than you see most other places in the world, except probably Japan. So this is the design accelerations for the importance of the building. And then when we work with this formula here and apply these values, and remember there's 3 values, the acceleration based on the seismic area, the type of soil, and the importance of the building. If you come up with where design acceleration is less than 1, all you have to do is EN 8120. You don't have to do anything anything special. If you're between 1 and 2.5, you have to do minor corrective actions. If you're between 2.5 and 4, there's medium corrective action. And when you get into this seismic lift category 3, you have to do a lot of things in order to make them function properly, comply with the code. So category 0, we just have to apply with, EN 8120, 50. Category 1, you have to do things like prevention of the snag points. Usually it means running a little cable between the brackets so that they won't hook around. The machinery has to be located on the same side of an expansion joint. Never considered this before until I read the code, but it makes very logical sense. If you have an expansion joint, things are going to move apart. And then the counterweight has to have retaining devices, and usually these are steel plates that have the shape of the rail, so that even if the guide shoes fall off, these plates keep the counterweight in its rails. Protection of traction shivs, and that's so the ropes stay on the shiv. Compensating chain guides and compensating rope guides so that they don't become a problem and get loose. And then precautions against environmental damage, and this applies primarily to hydraulic elevators. And then the guide rail system has to meet higher standards than it would normally meet, because you think about you're permitted 5 millimeters of deflection on a main rail, 10 on a counterweight. What you find when you go seismic is your counterweight rails have the same profile as your main rails typically, because you don't want them to deflect. And then the machinery has to be tied down. Then if you go to and then you have to look at the electrical installations in the hoistway. We talked before about limit switches and slow down switches. And then we have to provide information on how to use all of this to the owners. Then if you're in this category 2, you need car retaining devices. This is to keep the car frame in the guide rails. You have to have the car doors locked, so that one of the concerns is that if car doors come open and be in a bad position, it wouldn't be so good. Special behavior in case of power failure is written into the code. And then in category 3, you have to have a seismic detection system. Usually it's some type of an accelerometer. You have to have a seismic operation mode. The one I'm most familiar with is in California. We shut down the elevator completely, and then if everything is still able to run, we move the car to the nearest landing in moving in the opposite direction of the counterweight so they don't collide. And then there's an optional primary wave detection system. And I think if I were a consultant, I would recommend this on every installation. The primary waves are the first waves to arrive at a building from an earthquake, and they're not the damaging waves, but they get there first. They're followed by these are called P waves, S waves. Secondary waves are the ones that do the damage. They get there a little bit later. So it would be better to spend the extra money to get a detection system that would shut everything down, and preempt the damage. And it's optional, but I think the consulting community should probably recommend this. And if you're in this category 3, it's well worth the additional cost. So conclusions on EN 8177 are earthquakes are a serious problem in seismically active areas. There are costs associated with addressing this problem. It's going to raise the cost of a new lift installation if you're in a seismic area. It's not going to be the same. It's going to be more money. And each category you're in will be even more money. So if you're in someplace like Greece or Turkey, your lifts will be much more expensive than they would be here in Northampton, for instance. And there are serious consequences for ignoring this problem. But EN 81 addresses this issue quite well. Now, EN 81 there's a prEN 81 that has some modifications to this. Generally, it's approximately the same. There's some subtleties that are important, but the general concepts of what I presented are still the same. I don't know if the prEN has become a full. No, it hasn't. Okay, it's still in the PR stage. So, thank you. Questions?